So welcome to the final lecture for the course. I'm going to discuss photometric redshift estimation and focus on some of the statistical challenges and procedures that are involved in redshift estimation. So first, a little bit of background on photometric redshift estimation. I think we briefly talked about this in 2 lectures earlier, but just so that we're all on the same page. So on this plot is a spectra for an object, and the red line, this is the spectra that you might observe with an instrument. So a spectra is the brightness of an object in flux as a function of wavelength of light in angstroms. So the red line is the observed flux. That is a redshifted version of the true spectrum. So the blue line here is the true spectrum, which wouldn't be observed. And effectively, it's just a shift here. And the shift is defined by this equation. So given data like this red curve, what we'd like to do is estimate Z, estimate the redshift. And so redshift is caused by the fact that an object may be moving away from us, and that's causing the wavelength of light to shift. So estimating redshift is fairly easy if our data is a spectra, like this red line, because we expect there to be certain features in the spectra. So in particular, this spike that we see at around 4,000 angstroms, we know that there should be a spike near 1,200 or so angstroms. So if we have a spectra for an object like this red line, it's easy to estimate this Z quantity, the redshift. The challenge is that we only have spectra for a very small fraction of objects. So in the first 3 lectures of this course, we talked about time domain data and about getting photometric observations of objects. So typically, that's what we have. We have photometric data for objects. So what is photometric data? Photometric data is essentially the spectra observed at a set of wavelengths, or integrated across a set of wavelengths. So here's an example where there's an object which has this blue kind of spiky line spectra. So if we have a spectrograph, we would observe this this blue line. However, if we're taking photometry on this object, instead of this very dense grid of lines, we would just observe the spectra integrated across one of these filters. So we'd get 5 measurements. Instead of having, for this object, a few thousand measurements, we'd have just 5 measurements for this object. So that's photometry. And in the first 3 lectures, we talked about time domain astronomy, where we collected photometry over time. Today, we're just going to be talking about where we collect photometry at a single time in a set of filters. So in this case, 5 filters. So since we're able to get photometry for so many objects, that's great. What we'd like to do is, using just this photometry, go back and actually estimate the redshift, Z, for the object. However, this is now much harder because we don't necessarily see where these spikes are, and we can't align the observed spectra with the lines where they should be in the true unredshifted spectra. Does that background make sense?
So we observe the entire range of wavelength of light, but if we use different filters, does that mean for I filter, for example, we observe wavelengths between 7,000 and 8, yeah. So we observe that range of wavelengths.
We observe one measurement within those wavelengths. So essentially, you would take the spectra and multiply it by this filter So this filter could be on like a 0 to 1 scale. So you'd take the spectra, multiply it by the filter, which is telling you how much light at that frequency is being transmitted into the telescope, and then you would sum that all up. So you only get, if you have these 5 filters, you only get 5 numbers for this object. Whereas if you had a spectra, you generally have these spectra. There are bins here for the spectra, but they're very, very narrow. So you'd have thousands of brightness measurements for the object. So if you have thousands of brightness measurements, you have the spectra, easy to estimate the redshift Z. If you have photometry with, say, 5 bands, now much harder to estimate the redshift. But if you can do that, then you can get redshifts for very, very large numbers of objects. So surveys in astronomy are getting photometry for billions of objects, or certainly hundreds of millions, maybe soon to be billions of objects. And then if you have that, if you have good methods for estimating redshifts, then you can get redshifts for a lot of objects. Whereas you just don't have enough instruments to collect spectra for them all. Okay, so one approach that you can take to addressing this problem is to do sort of machine learning. So suppose we get photometry on a set of objects. We can, and we observe those objects through some set of filters. We can then get spectra for those objects, get the redshift from those for the objects which we got spectra for, because that's fairly easy. And then we have essentially a training set, and then we can build some model on that training set, and then apply that model to all of the objects which we didn't collect spectra for. So just as an example, here, this is some data. I think this might be Hubble data. It's data that is observed in 7 filters. So here are the different filters illustrated by the lines. So these are telling you what wavelengths you're seeing the spectra in with those filters. And then for 100 or so objects, we have the magnitude of the brightness of the object in those filters. So I'm showing 4 of the 7 filters, scatter plots for 4 of the 7 filters here, along with the redshift, which we know because we actually spent some time to get a spectra for these objects, and then we were able to very accurately estimate redshift. So the idea would be to use the data here to estimate the Z. And you can see there's at least some relationship between the photometry and the redshift. You can also see that there's more between adjacent cells here. The magnitudes are more correlated. That's because these filters are closer to each other. So, for example, IRI-MH and IRI-MJ, those are both like out here. So the spectra is somewhat constant across that area, whereas there's more scatter between filters that are further apart. Okay, so very simply, I built a random forest prediction model on that data, and made some predictions. So on the x-axis here is the spectroscopic redshift, which you can think of as being ground truth. And on the y-axis is the random forest estimated redshift. It's doing a maybe okay job. A lot of times the quality of the redshift estimate is measured as the residual divided by 1 plus the true redshift. So the residual would just be the difference between the points here and the vertical the identity line. So it's residual and then divided by 1 plus z. So I compared the random forest in the which is the black density here, to just random guessing. So if I just took the mean of all the redshifts of all the objects, that would be kind of randomly guessing the redshift for each object. And you can see that you're doing a bit better than that. You're closer to 0. So this is one approach, or more sophisticated versions of this are one approach to doing photometric redshift estimation. There's a few problems. One is that these are ignoring uncertainty in the photometry. So I didn't plot the uncertainties here, but there were actually uncertainties on all of these points. So that was not incorporated into this method. The second issue is that the training sets that you get tend to be for nearby objects. That's because in order to get spectra for far away objects, your instrument, your spectrometer, has to spend a lot of time looking at those objects because they're so dim. So what you end up with is training sets that consist of usually nearby objects and unlabeled data sets or test data sets that consist mostly of far away objects. And the intrinsic, the spectra for far away objects actually looks somewhat different. And there are different types of objects that you'd expect to be far away. So you get essentially a bias sample. And then it's somewhat difficult to compute uncertainty on your redshifts here, random forest, and most machine learning methods don't output really nice like posteriors on parameters. Okay, so what I'm going to do for the next several slides is talk about one method for photometric redshift estimation called EAZY. It's EAZY Accurate Zphot from Yale. So Zphot, Z is the typical symbol for redshift, and Zphot is photometric redshift. So this work synthesizes some ideas from previous articles. And I'm going to give a summary of some of the statistical aspects of what they do with EAZY. I think it's one of the more popular photometric redshift estimation tools. So what goes on in EAZY and in a lot of other photometric redshift estimation methods is to develop a model for what the spectra look like. These are often called templates because the model is really just a set of spectra. So these spectra I'll denote with the symbol TI. These TI could come from several sources. One could be that you actually observe spectra for a lot of objects, and so you have some idea about what spectra look like. That's good in the sense that then you have real data. The problem with that is it can be hard to actually get spectra for far away objects. So these templates could also just be output from physical models and simulations. Okay, and so TZI is going to be the template I shifted by a redshift of Z. And then TJZI is going to be template I redshifted by Z and then convolved with a particular filter J. And then for a particular object, you have a set of fluxes Fj and uncertainties on those fluxes sigma j. And one way to estimate redshift is just assuming a Gaussian error measurement model and doing maximum likelihood. So that leads to the optimization function at the bottom of the slide here, where you, for a particular object, so a particular object would be a set of Fj and sigma j. You're just finding the redshift and the template that minimizes the weighted sum of squares. So that works okay. There's a few problems with that. One is that you have to do a grid search over two sets of parameters. You have to do a grid search over the redshift Z, and then you do sort of a grid search over all of your different templates TI. So a nice generalization of that is to, instead of just assume that the spectra of the object you're observing is like one of your templates, instead you assume that it's a linear combination of your templates. That's in general going to be a more realistic assumption. So you're essentially expanding your set of templates here by considering a linear combination of them. Some sort of caveat here, though, is that you're going to want your linear combination, all of the coefficients, to be positive. So typically, these templates would represent something like a star-forming galaxy and a quiescent galaxy and a dusty galaxy, and the object that you're observing is going to be kind of somewhere in between those. So it's going to be a bit of one and a bit of the other. So you want the coefficients on this linear combination to be positive. So the optimization just becomes replacing this sort of grid search across a lot of templates with a minimization across this vector of coefficients alpha. This would be standard least squares at a fixed z, except you want the alphas to be positive. So in statistics, this is typically called non-negative least squares. Have people seen non-negative least squares? No? Half? OK. OK, so this is sort of in astronomy notation. So if we put this in statistical notation and get rid of the issue with minimizing across z, then we just have the standard least squares objective function, but with a constraint on the coefficients that we want them to be positive. And then here, x is our design matrix, n by p design matrix, and y is our response in Rn. If we had this objective function but without the constraints, we'd just be in the sort of OLS framework and with the familiar solution for beta. All right, so just an illustration of non-negative least squares and a little bit of a warning about using it. Or thinking about the minimization. So I simulated a little bit of data here. That's these black circles, and then fit the standard OLS line through them. That's this black line here, and you can see that the slope is clearly positive for the black line. However, the y-intercept is negative. So this black line cannot be the non-negative least square solution because one of your coefficients is negative. In particular, beta 0 is negative here. So a natural thing to do would be to say, well, I can keep my slope, but just increase beta 0 up to 0, and then I'll have two coefficients, both of which are non-negative. So that's illustrated by this blue dotted line here. It has the same slope as the black line, but the y-intercept has just been shifted up to 0. So this blue dotted line, it is it's in the feasible set in the sense that the coefficients are non-negative. However, if you sort of take a bit of a look here, it doesn't actually look like it goes through the it doesn't look like it's going to minimize the sum of squares among minimize the sum of squares between the line and the points. In particular, if you shift the slope down a bit, it looks like you go through more of the points. So from if we look at what's going on with the likelihood, you have a sort of a feasible set of solutions, which are solutions where your coefficients are positive. So now on the x-axis is beta 0, and on the y-axis is beta 1. And the gray region is the set of solutions that you're willing to consider to the non-negative least squares problem. The black point here is the OLS solution. And naively, you might just take the OLS solution and then set the y-intercept to 0, keeping the slope the same. However, as this likelihood survey shows, that's actually not the best thing to do. You want to, at the same time as you increase the y-intercept up to 0, you want to decrease the slope. So that was going on here, that you increase the y-intercept but decrease the slope is going to give you a better fit. So there's a bunch of packages for for fitting non-negative least squares. In R, there's NNLS, and in Python, there's SciPy optimize NNLS. Those both use the active set method. This EAZY code, which does the non-negative least squares fitting in order to find a linear combination of templates, uses an algorithm by Shah. Is that all clear? Okay, so that's the first statistical issue that's addressed in EAZY. The second issue is non-negative matrix factorization. Has anyone heard of non-negative matrix factorization? No? Okay, so we're at 40%. That's about right. Okay, so we need this set of templates, and then when we, for data, we're going to fit some linear combination of those templates to it. And we're going to make sure that the coefficients are non-negative. So we can have these templates, these TI templates. They can be observed data, or they can be output from simulations, and there are disadvantages and advantages to both of those approaches. It's nice to have a reasonably small set of TI. One is that there's easier interpretation for what these TI mean astronomically. If you have 10 TI, you can look at each of these templates as representing kind of a different type of galaxy. Whereas if you have hundreds of them, there's kind of a lot of continuity there, and you may not be able to really pin down what each TI is representing. The other advantage to having a small set of TI is that computation is going to be faster, because when you're fitting this NNLS algorithm, it's nice to have a smaller set of TI. So here's maybe an initial set of templates that you might consider. So there's 259, this should say templates. So 259 templates here. And it might be nice to reduce this set through some dimension reduction method. Okay, so we can think of these templates as being a matrix X, in an N by P matrix, where N is the number of templates, the initial number of templates we might be considering, and P is the number of bins for each template. So P would be however many times these templates are observed, probably a few thousand. And then there's 259 total templates. So oftentimes when we have high dimensional data, the data is actually lying on some lower dimensional subspace. And what we'd like to do is find that lower dimensional subspace. So that's called dimension reduction. So in general, the most common tool for dimension reduction is principal components analysis. In this case, we would like to have positive basis. So when we find a set of 3 basis vectors for these templates, we want them to all be positive, because if they're negative, there's really no interpretation of that as a spectra for an object, because spectra must be positive. So this just gives an example of like why you might think the dimension is much less than P, which is a few thousand. So if you plot the template values from the first coordinate against template values from the second coordinate, you can see that they're pretty highly correlated. So this is just going back here. The first two coordinates plotted against each other, and they're highly correlated because these are continuous functions. Okay, so we could apply PCA. That would be the maybe go-to dimension reduction method. So the idea behind PCA is that we realign the axis so that the most variation in the data is along the first axis, and the second most variation is along the second axis, and so on. And the idea is then that for the higher axes, we can ignore them because there is so little variation in those directions. So typically, we apply PCA to a scaled version of the data matrix X. So first, we would remove the mean, mu, and then scale the columns by the standard deviation. Sometimes this is not done, but often it is. And then the scale, the mathematical tool behind PCA is singular value decomposition. So we can decompose X into three matrices, each of which has a interpretation. For our case, the V matrix would be the most important. So these are the V matrix represents the new basis vectors in the PCA basis vectors, so the principal components. And then typically we only would preserve the first few components where we think most of the variation in the data lies. So we could preserve the first Q components. And X star Q is a reconstruction of X star using only the first Q principal components. And if the data actually does lie on a linear subspace of dimension Q, then this approximation or X star Q should be close to X star. And then we can recover the original data just by adding the mean back and scaling by S. So that's PCA. That would be the maybe go-to tool for this problem. But like I said, we would like to have a basis which is positive. So one tool for doing that for essentially.
So why do we care the interpretation of the template, the weights? They have to be positive. I mean, our goal is to estimate the redshift. So if our PCA can have an accurate estimate of the redshift, so does it matter? I think,
yeah, so that's a good question. I think it matters somewhat more to an astronomer who wants templates to have a physical interpretation. As a statistician, you might just say, make it a little bit more black boxy, and then you can say that on some data set where you have spectroscopic redshifts, you can say, look, I'm doing a great job at estimating those. If you want to have a method where you have a lot of interpretation for the different components, then it's nice to say I have 5 templates, and this template is representing like a starburst galaxy, and this one is representing a dusty galaxy, and this is representing something else. Because then you can people use this not just to do something like this, not just to do photometric redshift estimation, but also to say like what kind of type of galaxy this is. So if your templates have physical meaning, then the coefficients that you estimate for the templates will have some physical meaning, like how dusty or starbursty the galaxy is. But yeah, from a strictly prediction standpoint, it's not super important. OK, so if you do want to get basis vectors that are positive, the somewhat new tool for doing that is non-negative matrix factorization. So with non-negative matrix factorization, you decompose the data matrix X into two matrices, W and H. Here, everything should be positive. So X is going to be positive because these are the spectra. And then we enforce that W and H be positive. And H is going to be, the rows of H are going to be the new bases. So we would, before running this algorithm, we would choose R. That would be the dimension that we're going to project the data into. And then we can actually estimate W and H by actually putting a model onto this. So we can think of the Xij as being Poisson with a rate of the ijth component of WH. That then suggests doing maximum likelihood, and the log likelihood is proportional to this objective function. Yeah, so the main benefit of this is that your basis vectors have more physical interpretation than if you do PCA. There are disadvantages. Optimizing the log likelihood is more difficult, and there are some identifiability issues with this model, where even if this model is correct, multiple W and H can produce X. Right, so just a little demonstration of this on some non-astronomical data. So MNIST is a famous data set for handwriting recognition. So there's in MNIST, there may be several versions of the data set, but in my version there's maybe 40,000 or so digits, and each digit is a 28 by 28 image in grayscale. There were 4,072 fours in the MNIST data set, and I just made plots of 12 of them here, so you can see different people's writing styles. And one thing, this is kind of high-dimensional data because it's each object is 28 by 28, so each object has 784 dimensions. So it can be nice to reduce the dimensionality of this data and look for low-dimensional structure. So I vectorized each of these images and then applied PCA and non-negative matrix factorization. And on the slide are the results for the PCA after removing the mean and then plotting the first and the mean and the first three principal components, and then the four basis vectors for non-negative matrix factorization. So a nice thing about non-negative matrix factorization in this case is that the basis vectors more closely resemble fours, and so have maybe more interpretation than PCA. From a reconstruction standpoint, though, PCA is going to be probably as good or maybe better. All right, we're cruising. OK, so then I ran the EAZY on the data set that I showed with random forest before. On the left plot here is the true redshift, spectroscopic redshift versus random forest estimated redshift. I showed this earlier. And then on the right plot is the true redshift, the spectroscopic redshift against the EAZY estimated redshift. So EAZY seems to be doing a much better job here. There are a few disasters in terms of errors. And then in terms of the looking at the residuals over 1 minus z, EAZY, the blue dotted line, tends to be quite close to 0, whereas random forest and random guessing aren't doing as well. They're much more spread. So those are two aspects of photometric redshift estimation, the non-negative least squares and the non-negative matrix factorization. There's also some other statistical challenges or some other problems that they look at in EAZY. One of them is accounting for template error. So you might feel that your templates are approximate, but that they're not accurately modeling all spectra perfectly, and in particular that certain areas of the template may be systematically worse than other areas. So the EAZY article has some methods for accounting for that, in particular downweighting areas of the spectra where the templates are not fitting well. So you can estimate areas of spectra where templates are not fitting well and then downweight those. The other thing that you can do is try to put this into more of a hierarchical model rather than using a totally separate set of templates to estimate the redshift for some given photometric data you have. You can actually use the given photometric data you have then to build up templates, and potentially those templates are more accurate for the data that you have since you're building them from your data. And then I didn't talk so much about propagating uncertainty on Redshift, but in EAZY, they work the non-negative matrix factorization and non-negative least squares into a Bayesian model, and that model allows them to get posteriors on Redshift. And then finally, this is a fairly important problem within astronomy, so there's been a lot of work on it. Unfortunately, most of it has been published in astronomy journals. I don't know of a great reference in statistics journals, but people tend to either take the machine learning approach, like this first article or this third article, or of a more Bayesian modeling approach with templates. The more machine learning approaches obviously do a more careful job than I showed on the last slide. So they are at least somewhat competitive with the modeling approaches, but clearly if you have good, if you're able to come up with good templates, that can give you much better results than kind of approaching something blind with a machine learning classifier. Okay. So that's all I have for today. If you have any questions.
So usually the data, how large the data would be for this?
In terms of the number of templates in this EAZY article, it first came out in 2008, I think, and they started with some big set of templates, but then they used the non-negative matrix factorization to get it down to like 6 templates. So not many templates, and then in terms of applying it to data sets, anywhere from a few hundred to maybe tens of thousands of objects. But once you're applying it to get redshifts for individual objects, it's embarrassingly parallel, so it's not too hard to scale up. More recently, in versions of EAZY, they have like dozens or maybe even hundreds of templates now. The goal is to get a template set that's going to match the type of spectra that you're going to see in your data, and depending on how far away you're looking, you'd expect the spectra of objects to be different. So the important part of photometric redshift estimation is getting good templates that match what you think you're going to see, and that's can be difficult.